All right, so let's take a look at the homework question number 6, again from worksheet 5.4. Now in this case, we have two springs, and the end of the two springs are attached and pressed towards each other. So they are 20 centimeters apart, as shown in the diagram. Now it says one spring has a spring constant of 120 newtons per meter and an equilibrium position of 16 centimeters. The other has a spring constant of 240 newtons per meter and equilibrium position of 12 centimeters. Determine how much each spring is compressed. So we can see that if you add the 16 and 12, we get 28, and right now there's only 20 centimeters between them, which means that both of them are being compressed. So first, let's identify the variables here. So let x1 be how much the spring 1 is compressed. Be how much spring 1 is compressed. Okay, so then we know if you take the rest or equilibrium position of 16 centimeters, we know that 16 minus whatever this is, x1, is going to be, the position that this is on the diagram, right? So we can say then its rest length of 0.16 minus the how much is compressed, x1, is going to be the length on the diagram, is the compressed length of spring 1. Right? So this corresponds to that length right there. Well, if you know this length here, 20 minus whatever this is going to give us the decompressed length of the other spring, because again, we know the total is 20 centimeters and we just expressed the length of the first spring that's compressed. Then 20 minus all of this is going to be the compressed length of spring 2. So the length of compressed spring 2, this right here, is going to be 20 centimeters. Notice 20 point, so this 2 sig figs is going to be 20 minus whatever this is, minus 0.16 minus x1. So then, how do you know how much it was compressed? Well, if this is the compressed length of spring 2, we know its equilibrium position is 12 centimeters. So 12 minus the compressed length is going to give us the length of spring 2. All right, so now that you know the compressed length of spring 2, all of this, we know that it has to be longer when it's uncompressed. So if you take the equilibrium position of 12 centimeters, we say that 12 centimeters minus the compressed length is how much is actually being compressed, or your delta x. So we're going to do, the next line is going to be our uncompressed length of 12 centimeters or 0.12 meters minus the length of the compression, which is all of this, okay? This is how much spring 2 is compressed. So this is going to be our x2. Okay, so you can call this your x2. So x1 is just the difference like that, and x2 is the expression with the x1. So basically combining two variables here and substitute it in already, because otherwise we would have two unknowns, x1 and x2. So we're using substitution here basically to come up with one equation with only one variable. Now let's simplify this a little bit before we plug it into our f-net equation. So let's take this equation down here and let's see what we can do here. Now in the square brackets we're just subtracting here, so we can just remove them and see what we get. We get 20. Here we get negative 0.16 plus x1. Right, so we can add them together. So this is going to be 0.08 plus x1. Let's simplify it one more time. Let's remove this bracket here, the square one. So we're going to get 0.12 minus 0.08 minus x1, and do the last subtraction here. So we get 0.12 minus 0.08 is going to be 0.04. Sorry, I made a mistake here. 20 minus 0.16 is 0.04. All right, so 0.12 minus 0.04 is going to be 0.08 minus x1. Okay. So we have our equation for how much the spring 1 is compressed, which is x1, and we know how much spring 2 is compressed, which is x2, which is basically what we just got here. So all of this is now our x2, right? So that's our delta x for x2 basically. So the next step is to write the f-net equations. Now in this case, what we're going to do is we're going to take our diagram here and introduce a point particle, which is basically a massless point. But it will help us set up the f-net equation. So let's make a free body diagram of this massless particle. So here's our particle, and in this case we have only two forces acting on it. We're going to have our spring 1 pushing it to the right. So let's say this is our Fe1, so the elastic force of spring 1, and then the spring 2 is going to push in the opposite direction. Okay, because this is just a point particle, massless, there's no gravity acting on it, so we can ignore any other forces. So these are the only two forces that we're going to care about. So let's write the f-net. In the x direction, we have our Fe1 minus Fe2 equal the mass, which in this case is 0. And because the springs are actually not moving, they're also at equilibrium. So in this case, we can treat like either acceleration is 0, or for this matter, the mass we're just considering as massless. So anyway, the right side ends up being 0. So we get the following. We get our Fe1 equal to Fe2. Right? Now we can replace this with the spring definition, this the elastic force definition, which is going to be our delta x times the constant. Now in this case, the delta x is going to be represented by our x1 in the first one and our x2 in the second one, which is the expression down here. So this is our x2 we're going to plug in. So let's say that this one is going to be our k1 x1, k2 x2. Now the x1 is just going to be x1, so we have to just plug in our k1 value, which is 120 newtons per meter. So 120 times x1. K2 is 240 times x2, and x2 is all of this, 0.08 minus x1. Okay. Now we have to expand this and basically solve for x1. Once you know your x1, we can go back to our definition for x2 here and find x2. So let's see what we have here. We have, we got to expand this side. Multiply this by that and by negative x1. So 120 x1 equal to 240 times 0.08 is 19.2 minus 240 x1. All right, so let's move the 240 x1 to the right side. We get positive. All right, added together, we get 360. All right, so again, 19.2 divided by 360, we get 0.53 repeating. I dropped to 0 here, so this is 0.053 repeating, which is in meters, but we need to change it to centimeters to make it maybe a little easier to understand. So move the decimal 2 points to the right, we get 5.3. So that's our x1 value. Now we do need to use meters in our x2 calculation though. Actually it doesn't matter, but let's do x2 now. No, we do need to use meters because this is in meters, so we'll plug in 0.053. So let's see what we get. .027 meters, or in centimeters is going to be 2.7 centimeters. So that's going to be the two values for the springs when they compress. So again, x1 was compressed by 5.3 centimeters, x2 was compressed by 2.7 centimeters, which makes sense because if you look at the constants, spring 2 has much higher spring constant, which means it's harder to compress it. So we expect that it will compress less compared to the one that has lower spring constant. And that's what we got. The spring 2 compressed only by about half of what the spring 1 compressed. So again, this is quite a challenging question. You have to do some algebra here and solve a system of equations, just like in the previous question.